a webinar session with Tebis CAD CAM 5-axis milling for trimming. Okay, so basically, why do customers choose Tebis Trim? We choose Tebis Trim for improved machine safety. We use full collision avoidance of the spindle, cutting tools, tool holders, and the finished part. Optimization of toolpath vectors and tilt directions. Templating strategy technology. We also have quick, easy toolpath corrections of modifications for design changes. Auto recognition of standard shapes with conversational output. Reverse post-processing for import of historical teach and learn programs. So as we go through the demonstration today, we'll try and touch on each of these points and make it quite clear Tebis' strong points. So initially what we have on the screen is our component and our fixturing all together. So we have our component in blue and we have our fixturing, which is all the rest of the part. Okay, so in the initial stage, what I'm going to show you is the preparation of surfaces, creation of curves, repairing of curves before we start the programming process. This is just so you can see how strong Tebis is on the CAD front and how quickly we can prepare a component for machining. Okay, so this is a solid model. We have an inner surface, we have connecting flanks, and we have an outer surface area. To make the programming process more simple, we're going to pull the inside surface off of this model. That way we can use that to drive the tool direction. So when we're working normal from surface, we'll have the tool direction always perpendicular to this surface. So just to see how quickly that works. And we're going to choose this. And what we can see also is within this operation, we can pull this away. This is just a visual movement, and what it allows us to do is see the area that we've removed from the initial model. We save this as topology on an active layer. Okay. So what we have now is just a singular sheet surface from the inside of the component. This will now allow us to create curves, which will allow us to start machining. So the next step is to create a curve around the external boundaries of this component. And it really is as simple as that. 2 clicks and we have a curve. Now, where we're dealing with solids, especially customer models and things like that, we can have some inconsistencies in the CAD data. So when we produce these curves, we can sometimes wind up with inconsistencies in the curve as well. Because these curves are being generated directly from the surface data, so what we have is the ability to repair these curves very simply. So we're going to choose the curve and apply. So what this box now does is it shows us all the potential errors that could be found within the curve. So reversals are where we have zigzags in the curve, and this will ruin our tool motion along the curve. Wrinkles similarly are perpendicular movements away from the curve. This will also ruin tool movement. We're highlighting mini segments. These are very small, tiny pieces of data along the curve. This can cause stuttering of the tool curve and some inconsistent movement also. And gaps, quite obviously, are holes in the curve. So this is areas that aren't joined together properly. This can cause a tool to jump out or get an incomplete curve or an incomplete cut. So as we look on this screen now, all we've got is 23 mini segments. To repair this, we just hit result, and that's it. The curve's been repaired. Again, a very simple, very easy to use single button operation. In essence, this is the entire process for preparing a model for machining. We've separated the lower surface, we've created a curve around the outside, we've repaired the curve, now we're ready to machine it. So now we can have a look at programming. So in our program manager, which is this area here now, we have a black layer. This black layer is basically where we predefine components for collision checking. So we can select the part, we can select fixturing, we define the machine. So in here, we have selected the components, we've selected the finished part and the fixturing underneath it. In this area, we've selected the machine we're going to be working in. This is important because Tebis uses the actual limits and rotational limits of the machine when it's doing a virtual machine check. And in here, we actually set the part up in the virtual machine as we would be using it. So this machine has got all the guards on it. It's got all the elements. Uniquely in Tebis, when we're doing collision checking using the virtual machine, we include all of the guards and the components, because if we have extended tools or we have an operation that goes very close to the movement of the machine, it is sometimes possible to hit some of these. With Tebis doing the checking and running the virtual machine check, we eliminate that problem. Also, you see in our virtual machine, we have the tool changer and we have the machine head up in the home position. Whilst most softwares will be able to check the component, check the toolpath, and check the movement of the machine, Tebis is also able to calculate and check off-part moves. So that includes the macros for tool changing. So if you have extended tools and a large part in the machine, we can also be quite sure that we're not going to have any collisions around the toolpath, around the tool change area. What we've also got on screen is the part set up in the machine as we would expect to see it. Okay, so on to programming. In Tebis, there's a few different ways of programming. We can program manually, bring in each operation individually, define everything from beginning to end, and run the toolpath. What I'm going to use today is a template. So basically all I've done is I've predefined a series of machining operations, which you can see here. And not for the first one, but for the second two, I've had Tebis pre-select the data. So by organizing the data using various colors and positions in the layer tree, I'm able to have Tebis predefine and pre-select the information that's needed. However, in this first operation, I'm going to select the data as I come to it. So I've pre-selected the tooling. My strategy is all ready to go. My leads and links are set, my safety value is set, and my technology area with my speeds and feeds is also set. All I need to do is choose the data I want to machine around. So I'm going to machine this curve and this component. So the curve will define the direction the tool is traveling, and the surface will define the direction that the tool is pointing. So the Z direction of the tool, the vector. Okay, so if I calculate that, what we can see on screen immediately is obviously our part. We can see our head has become visible because we're checking against this all the time, but we can also see the projected tool path with the tool vectors along it. So each of these yellow vectors will define the direction of the tool by putting that line up the center of the cutting tool. So what's quite important with Tebis is the fact that we have full head control. So where most softwares will give you axis control and rotational control, we can actually define exactly where this entire head component is through the entire programming process. So what is quite a common problem with our customers before they come to Tebis is where they're programming this direction and the angles needed, the software doesn't justify this head position, which means that they can have collisions as they go around the component. Now for this part, I'm going to flip the head to the other side, and we have full control, and we can move this head as and when we please to be able to control where the head is at all times, allowing for areas of fixture. So as we move through to vector manipulation. So vector manipulation allows us to define and move these vectors in a way to smooth the toolpath. So whilst we're here, we can make manual movements and manual adjustments to the toolpath. or we can predefine by just typing the value in. Okay, so if we take this toolpath from the beginning and drive this through manually, what we can see is as the tool comes around and comes up towards the vertical position, we start to get an unwind. As the tool then traverses down the long area, when we get into this corner, what we find is that we have a vector off at an angle, and this will cause the head to roll over. Now, the vector is in exactly the right position because we told the tool to stay perpendicular to the surface. But what we need to do is program this angle out so that we don't have to have the head tipping over with excess movement. So in Tebis, when we're controlling vector positions and we're controlling the attitude and direction of the tool, what we do is we create control points along the curve and then tell Tebis how to behave in between those control points. So if I put a point here and tell Tebis to run that at -180 and set that, we see the number 2 appear and the head spin around. If we then come to this point here, we can make this also -180. We see number 3 appear and we see the head position. Okay, all that's left to do is tell Tebis how to deal with this curve in between, or this movement in between. So we're going to vector interpolate. What this has done now is if we travel from point 2 towards point 3, we now have no rotation in the head because the head's already aligned. And what we also get is as we approach this area, we get no tipping of the head and it follows the vector downwards. So if we zoom right in, what the vector interpolate has done is created a vertical vector here instead of the angle one that we had previously. So using that strategy, we can go all the way around this toolpath and make these adjustments all the way around and get a complete toolpath. But for this instance, so we can see it running, there's a nice clean entry, nice constant head angles, nice lift. That's into our rigid angle, and then into the next area, making for a nice clean toolpath. Okay, so next will be if we were to have a drawing change. So if we have a change in data, or we have some extra data that's being handed to us, which in this example is this new curve here, rather than go through the process of redrawing our curves, reconnecting our curves and redoing surface data, what we can do is we can just add this in and Tebis will interactively take account of the new path and adjust accordingly. So if I add that curve in there, what you'll see now is that instead of Tebis coming across here and around the original curve area, it's gone up and around the new curve area. So as we make these adjustments, all of the previous adjustments we've made are already saved. So what we get now is the ability to build up a program that works perfectly as we go along the process. Okay, so one of the big issues a lot of our customers come to us with is the fact that they're using abrasive materials, whether that's a glass-filled plastic or whether it's carbon fiber. So one of the big strengths of path correction in Tebis is that if we create a set point here, we're able to start driving the tool up and down its Z-axis, the Z-axis of the tool. It will maintain the geometry of the cut path and it will maintain the direction of the cut path. But what we can do is we can adjust the depth of the tool against the component. What that'll do is spread the wear across the flute of the tool. So where the tool is at a certain depth, if you consistently cut around and around in that area, you'll get localized wearing. So not only is that inefficient for the cost of tooling, because you're wearing the tooling out very quickly, it also means that there's a lot more work needed to control the sizes of the component. So by moving the tool up and down the flute, what we're able to do is spread this wear up and down the entire flute, therefore prolonging the tool life and making more consistent parts, better quality parts. So if I come down to this next area here now, we can do some minor adjustments along the tool path. And this now gives us the sort of tool path that will spread the tool wear evenly along the flute, whilst also maintaining the cut geometry and the cut position of the tool against the component, so as not to lose any dimensional accuracy. Okay, so what we could do actually is see all of those changes being made and incorporate all of those changes we've made today now into one single program that works well and does exactly what we've asked it to. Okay, so the next set of strategies we want to look at today is 2.5D geometry. So as I've said before, this is all pre-selected. So all we have to do is go into the component. It's pre-selected the curves, it's pre-selected the surfaces, we're just ready to machine. So when Tebis recognizes a shape as being a geometric shape, whether that's a circle or a slot or a square or a rectangle, we can use Tebis to define this as 2.5D geometry. So quite simply what this means is, if we take a look at this circle, now if we were to machine this as a plane contour, what we get is a full 5 axis of movement. So we can see the head tipping down and rotating to cope with the angular change around the radius of the component. However, if we run this as a circle, what we can see is actually it just drops in, machines around in a circle. Now in this instance, this appears to be a bolt hole. So having Tebis machine it as a circle gives us nice parallel sides, gives us a more accurate cut than doing the 5-axis methodology. Also, 5-axis methodology can create long programs, whereas 2.5D geometry should create short, concise programs. And also, when using 2.5D geometry, we can connect this to the CAD cycles of your machine. So, for example, in the FANUC, we could use a G13 to create that shape. One of the other strengths in this is if we go to path correction, one of the other strengths of this is that although we're treating this circle as a circle right now, we can actually tell Tebis that it's a slot. And with path correction, we can actually machine a slot. So the advantage of this is quite a lot of design will have this as a bolt hole so that parts mate perfectly and we can just drop a screw straight through there. Obviously, in the real world where we're manufacturing components, we can have deformation of parts, we can have shrinkage, or we could just have a general losing of sizes and dimensions across vac formed parts or molded parts. So what we could do is we can add a slot into this now, so that any mating part that's screwed to it, we've got a little bit of adjustment space, a little bit of wiggle room to be able to get a screw in. So that's quite handy that although it is a circle, we don't have to define it as a circle. We can define it as a slot or a rectangle or anything we need to. So if we take a look at the next area in this slot, whilst also in path correction, because we're working in 2.5D, we have the ability to change the geometry and the position of this slot. So if we have a look at geometry first, we can change this slot to 120 mil long. We can also change the width to only 25 mil long. So if this slot was an eyeglass, it needs to line up with a scale, or if it's a slot that needs to line up with an Allen key head on a component underneath the cover, then we can make sure that the holes are big enough for it to line up. Also, if we have a part that's a mating part that fits into this, we can make on the fly adjustments just to make sure that what we're getting out of the machine is exactly what we need to get. Similarly, we can make these adjustments in position as well. You'll notice U, V, and W, which are incremental X, Y, and Z moves. So U, we're going to move 10 mil. So let's move the whole part over 10 mil. Y, we're going to put in minus 10 mil. We also have the ability, if the part has deformed slightly and we're not getting a full cut on depth, we can change the depth of the cut and change that path downwards. So we see the path is now 10 mil below the surface. But also, we have the ability to change the rotation. So with a combination of being able to adjust the geometry and the position, we can make sure that we're getting mating parts mating where they should and how they should every time. And this saves us having to keep redrawing geometry and keep remodeling the surfaces, and should make life an awful lot easier. Okay. So our last program now in this list is the large pocket area. So what we have is this large pocket. It looks like it should be a very nice tidy toolpath. We've got some nice clean vector movements. They're all pointing in about the right direction as we would expect. But if we drive the tool around, what we'll see is a lot of excess head movement. Now, this has just been generated purely because Tebis is trying to match directions and match angles. What we want is a clean, quick, simple process for tidying that all up. What we want is as little head movement as possible. That way we got the best cut, we get the best finished article, and we get the best tool life. So if we go to vectors, we can look at our first position, 10 degrees by 73.5. 10 degrees. So now we can see where potential problem is. So if we tie those two angles together, so the tool starts and finishes in the same position, and then go over to an area on the curve, we're going to do an A optimized toolpath. This will now prioritize the A movement over C movement. And what we should get is a nice movement with only the A axis moving. So that's tidied up the path an awful lot and should give us a much better result with a finished component. Okay, so what we can do is we can have a look at all three of these now running one after the other as a single program. With the inclusion of the fixture. So slows down a fraction. We can run this and we can see the program as it would come into the machine with all our changes of direction, all our changes of movement that we've added into it. What you'll see, especially with this slot, will be the change in position that we made. So we've changed the angle of the slot, the size of the slot, and the depth of the slot. And then on this last pocket, we'll be able to see a nice consistent movement with no excess head movement. Okay, so all I've got left to show you today really is our reverse post processor. So we've used our post processor to import this toolpath, which is a conventional 5-axis toolpath out of a machine. Whether it's a teach and learn program, a conventionally handwritten program, or whether it's a program that's been brought in from another software. What Tebis has done is it's brought in the drive curve, so we know which direction we're driving in. It's brought in the rapid moves for bringing the tool in and out of the component, and it's brought in the vectors to align the tool against. So, while we're at this stage of the program, although all these components have been brought in as a template, they're not rigid. So what we can actually do is use parts of the program, and what we could do is we could just change the geometry associated. So we choose a new toolpath. One out of that is that we have to change to a center-driven toolpath. So we're using the exact same program, the exact same cutting conditions, and we've also chosen to drive from the original surface, although we've chosen the new curve to drive against. So when we hit play, what we wind up with is our new curve, but now we have multiple vectors. So these vectors, the short ones are the Tebis vectors. So they're the ones that calculated this curve against the original surface. It also gives us an indication of how accurate the original program was. But if we go to vectors, what we can do is we can choose the vectors that we're the short ones are the Tebis calculated vectors. So we can choose the vector that's been calculated, and what we can do is we can align it to one of the original vectors. And as we work our way around the component, what we could do is create an exact replica of the original program, just by aligning these calculated vectors against the originally stated vectors. Okay, so the big advantage with this now is that once this process is complete, we're able to drive the tool exactly as it's being driven inside the machine. What that means is, because teach-and-learn programs are very difficult to modify, we have all these angular movements and a lot of difficult numbers to deal with. By doing this, we can then make adjustments to the toolpath contour. We can make adjustments to the finished final part. And it's a lot simpler and cleaner to work in Tebis this way rather than having to hand juggle code inside the machine. Also an awful lot safer. So that in a nutshell is the basics of the Tebis process. So if we go back to our summary. So in summary, we have improved machine safety. By using the virtual machine, we can collision check not just the tool and the holder like most softwares. We could check the tool, the holder, the spindle, all the rotational axes, the component, the fixturing, and also the external parts of the machine as well. We can optimize toolpath vectors and tilt directions. As we saw, we can manually move the head around. We can change angles as we need them. We can define which side of the cut the head is held at. This is very important for asymmetric headed machines. We then have templating strategies. So templating strategies will allow us to bring in predefined machining operations. We can work within company standards and company processes. We have quick, easy toolpath correction and modification design changes, so we can add geometry, remove geometry, or change the way that we treat geometry as we go along. We have auto recognition of standard shapes. So with our 2.5D geometry, we can create much simpler, much cleaner toolpaths using CAD cycles. And we can also change the way Tebis treats those. So we can convert circles into slots, and we can convert slots into squares if it's needed. And this is all done on the fly without the need for calculating or redrawing contours or redefining the part itself. And lastly, we have reverse post-processing. So we can import a existing toolpath from a teach-and-learn program. We can realign it with Tebis. We can recalculate it using Tebis, and then we can make any adjustments to that toolpath just as if it was a normal toolpath that we calculated from scratch. So basically, I'd like to thank everyone for turning up and listening to me, tell you guys about trimming applications. Hopefully you've seen some stuff that you like. If you want some more information, feel free to contact us at tebis.com. Alternatively, contact us directly at Tebis UK or Tebis USA using the contact details on screen. Thank you, guys. Take care. Bye.